techniques, and we are particularly going to look at data-driven approaches to localization. Right? How can you use uh, features other than just ranges? Because often ranges might not be a feasible idea to compute. So we basically rely on other signatures, which we call data, and the localization is based on fingerprinting those kind of data, or built on using machine learning techniques that are used on such data. Okay, so before going on to the data driven techniques, we are first going to touch upon relative localization, where we already had this pipeline in our minds, where we learned about the techniques that involve computation of ranges as well as location of the anchors, right? So we knew that how these ranges were computed, right? In details, we studied about computation of the time of flight or time of arrival, and apart from this, right, we also looked at other techniques that involve ranges like time difference of arrival, which is basically difference of ranges, as well as the angle of arrival, where we were trying to look at the particular angle from which the signal was arriving on the client, right, on the device. So one common thing that we sort of assumed in all such cases was the information regarding the anchor. Right? If you remember, both time difference of arrival as well as time of arrival, angle of arrival, they will require you to have detailed information regarding the anchor. Right? In particular, where they are present or where they will be deployed, right? If the system is going to be deployed. So this requires a lot of human effort, right, for performing deployment and such calibration tasks, right? This is not something you can just go. It's like a plug and play, right? Wherever you go, you can instantly deploy such a system. It doesn't happen because if you even plan to deploy such system, you need to do a pilot study just for planning the deployment. Okay, so the deployment cannot be arbitrarily done. You need to make sure, for example, the geometric dilution of precision, right? The metric that we spoke about, that is sort of good, right? And wherever you are placing the anchors, then you also want to make sure that the signal is reachable, right? You want to make sure that there are not a lot of obstacles that are present near the anchor, right? So apart from that, you also need to mark the location of the anchors in the coordinate reference frame that where you are deploying the anchors, right? You have to define an origin, which is 0 0, and then you have to do all the measurements and place the anchors at a certain location and know the coordinates of that particular location. And if you are doing it in 3D, it becomes more and more challenging, because you have to keep track of the third dimension also. Okay, so I specifically focus on situations where this is not an option, or often this is impossible to do, where we require in situ localization, right? Wherever we don't have any infrastructure and suddenly we need the service of localization, and that happens in disaster scenarios. Let's say there is a building which is on fire, and firefighters enter the building, and they do not have any infrastructure that is already present, and neither they have the scope to deploy any infrastructure and calibrate them, right? So this will be very much impractical from their side. So they kind of rely on localization, which will not have the anchor locations to start with, right? So there are like a series of works or techniques that are developed where they are just going to focus on the relative localization among the nodes, right? If you, it's not just one node, but you might have a system of nodes, right? And all we care about is to figure out their relative orientation or their relative locations. Okay, so what they will do is first you need to compute the range among these devices. Okay, so these are the node IDs, which is basically these are the devices, and they do not have any specific anchors or beacon nodes, right? Because it's not possible for you to deploy them or mark them, right, where they are. So any node, you can call them a device or a beacon, right? So there is no specific marking that this is a device and this is an anchor node, right? And what we start with is basically a range matrix or an Euclidean distance matrix. So if it computes the distance in between the node I and j. So if there is a fourth node, let's say this one, so the distance between the fourth node and the sixth node is this, right? Let's say here, this is a random example. It might not uh, satisfy all the triangular inequality stuff. It's just some made up numbers I presented here. But the general intention is to show you the flavor of this matrix, right? This matrix is going to have these numbers, right? These values, and this will be a symmetric matrix. So these numbers will be all repeated in this part of the figure. Okay, so if you have this information, if you have this complete information regarding the ranges in between all such nodes, what you can do is that it's possible to create the topology of the nodes, right? Suppose there are 8 nodes and we are interested in knowing the topology of the nodes or the relative orientation of the nodes, also known as relative localization. Okay, how are all given one node? Let's say you mark this as origin now. Let's say this is your 0 0, then you can definitely figure out the location of the other nodes in the 2D space. This is also known as 2D embedding, and typically the method that is used for going from the EDM or the Euclidean distance matrix to the topology is known as MDS or multidimensional scaling. So this is a fairly common fairly common methodology that is used in machine learning literature, where it's often required to know relative clusters, right, in the 2D space, right? If you have pairwise distance in between various features, let's say, or various entities, and you are interested in knowing if you kind of lay them down on a 2D plane, how do they look like? Okay, so this is often known as two-dimensional embedding, and this has applications in natural language processing, in other machine learning aspects, other machine learning application as well, right? So this is a fairly common technique. I'm not going to go into how exactly the technique works, but this is something that you can simply refer to any ML textbook, or even Wikipedia will also have a very nice derivations or applications of this technique. So you can refer to that, right? So what is kind of interesting to note, right, in our case, is the number of range measurements, right? If you see, if you look at the Euclidean distance metric, you actually need order of n square, right? You have n nodes, so you will have nc2, n choose 2 range measurements, which is order of n square, right? And this is fairly a large number, given that all this ranging cannot be done simultaneously, right? So because they are sharing the same wireless medium, and you already have fairly good amount of idea about how the ranging works, right? How the time of flight computation works, right? So this is, as you remember, this is a pair by pair basis, right? When the node number I is ranging with node number j, other nodes has to remain silent, right? Because they are going to interfere with the wireless medium or the wireless communication that is already going on in the medium, right? So you cannot do that, right? Otherwise, all the channel impulse response data from where the time of flight is estimated will be garbled, right? So you cannot really use them, use all the ranging in parallel, right? You have to do it in a sequential way. And whenever you do it in a sequential way, doing all this NC2 ranging computations will take fairly a large amount of time. And this is fine for static nodes, but if these nodes are dynamic, right? If they change their locations, right? Nodes change their locations. Nodes change locations. Then you have to do it like relatively fast, right? Otherwise, all these ranges will be very inconsistent, right? When one ranges with 2, you will have this data, whereas whenever you are doing one is ranging with 8, right? So you get this 14, whereas this number has changed by that time, right? It may be let's say 17 by the time when you are ranging one with 8, right? So This is a very fast changing matrix in case of a dynamic network, right? So you need to make or keep the Euclidean distance matrix as fresh as possible, right? And for that you cannot really do all the n square measurements. Okay, otherwise you'll end up having something very inconsistent, and just for some statistics it will require at least tens of milliseconds, right, in order to complete one ranging operation. You cannot really do it in like some millisecond. There will be some time that will be spent for processing and scheduling the packets and so on. Right? So there will be some amount of delay, and then you cannot do hundreds of ranging operations in a second, right? It's not really possible. Okay, so you have to remember this, right? If you have a Euclidean distance matrix which is actually complete, then only you can apply this MDS. Okay, but you, at the same time, you also appreciate that there is a problem in getting all these n square ranges. So we'll see what are the different things that can be done, and also make sure that since this is relative, right, this entire topology can be freely translated, rotated or reflected, right? It still preserves the properties of the EDM. So the EDM doesn't change if you do a rotation, translation or reflection of this matrix. Okay, so now in many practical cases what might happen is you have an obstacle or a certain range is so it's certain, the distance in between two nodes is so large, right? It is infeasible to range those two devices, right? So in those cases it might happen that you have missing ranges. And what is the problem if you randomly miss out a range? The MD, after doing an MDS, right? Let's say you try to guess or fill in some of those missing entries and perform a multidimensional scaling. The topology that you might end up with is non-rigid, right? What is non-rigid? If you see this portion of the figure, right? This can actually be flipped to another side, right? So this is doesn't become unique. Okay, so we call it non-rigid, whereas in the last case where we had a complete EDM, this was a rigid construction, right? There was no ambiguity about the position of the nodes, right? In this, whereas in this case, you can very easily see that the node was originally here, and you could simply flip the node in this side, right, which makes the entire configuration non-rigid, right? So the relative localization is not going to be sort of satisfied, right? The relative position of the nodes change, right? If you are able to flip a certain node on the other side of the graph, right? So what we need to do is that we need to ensure rigidity or uniqueness of the graph, right? So what needs to be done is that we need to at least make sure that we have the critical ranges, right? Even if we don't have all the ranges in the EDM, it is necessary that you have the critical ranges in the graph that ensure rigidity of the entire structure, right? So what does this mean? It cannot be, there is no ambiguous location of any node. There is no node that could be actually flipped without violating the EDM. And it appears that you do not require all the entries in the EDM to calculate a rigid transformation of the graph, right? It is only the critical ranges. So that is one of the problems to figure out which one of those ranges are critical, right? So there are certain ranges which might not be actually required. Still, it creates or still it constructs a unique of rigid graph. Okay, so this mostly goes on to the theory of rigidity. Okay, graph rigidity. Okay, so where we need to ensure that what are the ranges that has to be there in order to make sure that the graph is rigid. Okay, and the rest of the things, right, the rest of the items here, they could be predicted. Okay, so often we can say that if this 34 and 98, right? So let's say these are the and then we have these two things, right? This 78 and 64. So these are the this were the critical edges that were missing when we spoke about the missing ranges in the last slide. So if you fill in those, right, this can define a rigid graph, right, hypothetically speaking. So if this ensures a rigid graph, you can very easily compute the other ranges, right? It doesn't define, let's say, the ones that are red here, right, does not define the rigidity of the graph anymore, right? So the rigidity is already defined by the other ranges. So it's not true that you will require all of them. You might require only a few of them, but you need to make sure that those few are responsible for making the graph rigid. Okay, and then doing an multidimensional scaling operation on top of the EDM or the Euclidean distance matrix, you can create the relative localization of the nodes. So this is what you have is known as the relative localization of the nodes. Okay, so all of the nodes can be located given that you define an origin with some of the nodes, right? Let's say some node you assign as an origin, so you can define the rest of the nodes with respect to the origin node, right? And apart from that, you also have to make sure that you need to define a level of rotation, right? So this entire system of nodes could be rotated freely along this as the along this origin, right? So that is also that also still preserves the relative localization of the nodes, but you need to have this in mind that even if you have the relative topology constructed and let's say the origin not defined, you can always have rotation, translation, and reflection of the nodes. Okay. So this is one reference paper, right? If you want to get into the details about how relative localization works, in particular, how the MDS algorithm could be applied in order to construct the relative topology, you can refer to this particular paper, right? This is like a highly cited paper, and this also has some tutorial content so that you understand the technique. Okay. So now we did look at two different kinds of techniques. Both involved ranging, but one was without infrastructure. One was with infrastructure. So the left hand side, we knew the coordinates of the anchors. So anchor coordinates known, right? Whereas in the right hand side, we still had ranging. We created the Euclidean distance matrix here, which was ranges in between the ith and the jth node, but we did not have any concept of anchors or any location of the anchors to start with, right? Everything was relative. Okay, so there were no anchors, and let's say we don't know location of any particular node. Okay, so this was more, I would say, calibration free. There was no calibration effort that went in. Calibration free. Okay, and this was mostly, there were two things, right? One was the matrix completion, so trying to figure out which are the ranges that are essential, and apart from those ranges, you have to predict the rest of the entries in order to make the matrix complete. So that was a part of the matrix completion, and then we also looked at the technique called multidimensional scaling, which was creating a two-dimensional, in our case, a two-dimensional embedding of the nodes. Okay, and apart from these analytical approaches, you also have these data-driven approaches that I was going to talk about. These are like statistical or data-driven approaches. One is fingerprinting. So this is what I'm going to discuss today. So this is where you need infrastructure. So like wherever you needed the anchors, right, to be deployed, this one also requires infrastructure. And in terms of infrastructure, it is mostly referring to collecting such fingerprint data, building models, and trying to create training the data, right, to create machine learning models in order to predict location. So this is purely looked at as a location classification or location prediction problem. Okay, whereas in the earlier case, this was purely an analytical approach with the ranges. Okay, and the other thing, right, which sort of is infrastructure free in the sense you do not need any uh, deployable infrastructure. So you just carry a IMU sensor, an inertial measurement unit sensor, which is already a part of your smartphones, and robots will have them, right? So this also can provide you some level of positioning for some amount of time, right? So IMUs do drift, right? It has to be corrected, but for a short while, IMU could be used, right? So whenever, let's say, in between the time a device is not ranging, right? So as you saw, if you have a system of n nodes, there will be a certain delay before computation of the range, like in between computation of two ranges, right? And in between those times, right, IMU could be used for support, like to support the localization of those nodes in motion. Okay, so this is one more technology that we'll take a look in the next class briefly. Okay, so let's look at the concept behind fingerprinting, right? And in particular, what is RSSI, which is primarily used for such fingerprinting operations. Okay, so whenever there is a signal that is transmitted from the access point or the base station, uh, it is always transmitted at a certain power, right? Whenever any packet that you send out, it is transmitted at a certain power, and whenever it is received uh, at a certain frequency, right? Because all this wireless communication takes place in various frequencies in various channel widths, right? So you will see a certain power that is received because of the reception of the packet, right? So this is known as the received signal strength. Okay, and this received signal strength has a relation with the distance. Okay, so how far the receiver is, right? More the distance of the receiver, lower will be the signal strength of the received packet. Okay, so the relation sort of looks like this, right? I'll come to the point why log is taken here, right? Normally we just take simply distance, and there is this RSSI, right, which is a received signal strength indicator. I would prefer to use the term RSS, which is received signal strength, right? Indicator is basically a mapping of the received signal strength, let's say from 0 to 10, right, or 0 to 100. Right, so we can use both of them. There is some map which is created from RSS to RSSI, but the point to note here is that while you are very close to the transmitter, the received signal strength will be very high, and as you sort of go far and far, the received signal strength goes down. Okay, and the point here to note is the reason we took this logarithm in the distance is because if you look at the logarithm of the distance versus the RSSI or RSS, which is measured in dB here, right? In the absolute scale, it will be some dBm actually. So, okay, so we compare to in milliwatts, right? So this will have an approximately a straight line relation. Okay, so this is sort of linear. If you can imagine, there is a straight line which could be potentially drawn through these data points. Okay, and that is the reason we take a logarithm here. Okay, so one question here is that if you do not take log into account, right, how will the signal decay be? Like how should it ideally look like? Anybody wants to attempt? Hello.
Yes, sir,
So sorry, can you repeat?
you're audible. Sir.
Hello, I'm not audible.
No, sir, you are audible.
Okay, so how will the signal, how will this particular graph look like, right? Instead of taking a log, if you take simple distance, what will be the relationship of the power or the received signal strength versus distance?
As the distance increases, the signal strength decreases. It is indirectly proportional, sir.
No,
Inversely
decreases.
proportional.
In this case also it decreases, right? Decreases how? Okay, it decreases exponentially, right? You have
Yes,
taken a
yes.
logarithm. It's a very simple question.
Yes, sir.
Okay.
Sorry. Yeah.
I mean, that's the reason you want to take a log so that it looks linear. Okay. So the formulation is like this, right? We call it path loss. So what is path loss? Path loss is the amount of power that is actually lost, right? So from the starting, let's say from the starting point. So suppose the power at which it was transmitted was ptx, right? And it was received at a power like prx, right? So ptx minus prx is basically the path loss. How much of the power was lost because of uh, the journey of the signal. Okay, so this is called path loss. Okay, so we try to compute what is the path loss if the signal travels a distance of d. D could be d meters. Okay, so and this is proportional to d by d naught to the power n. So this is a reference distance. Okay, this is a reference distance, and n is something which is known as the path loss exponent. Okay, so this is called path loss exponent or path loss coefficient and so on. So you all are aware of this inverse square law, right? Any let's say the power which basically decays as 1 by t square, right? So if you take log, right, in the dB scale, it basically becomes path loss at distance d is equal to path loss at distance d0. So this is something that is that needs to be calibrated. So what is the path loss at a reference distance? Let's say what is the path loss at distance of 1 meter or 10 meter, right? That is something that is already known, right? Path loss at a reference distance plus 10 n is the path loss exponent. It could be typical values are like 2 to 3, right? It will vary between like let's say 2 to 4. If you have obstacles and if you have a lot of foliage and so on, the path loss will be more, right? And if you have completely free space, right, complete line of sight, it is closer to 2. Okay, so 10 n log of d by d naught. Again, d naught is the reference distance. So that is how you can compute the path loss for a given signal, right, given the distance. Okay. Now what we will see is if you simply fit a straight line, right, using let's say ordinary least squares, this is like a linear regression we do, and in this way you can figure out the slope of the straight line as well as the intercept. So basically this gives you a formula to figure out what will be the path loss at a certain distance d. Okay, so why we are trying to do this? We now since we are not able to calculate ranges directly, can we use the RSS data or the value of the RSS as a proxy to figure out the distance from the transmitter? Right now you can think this becomes an imaginary anchor, right? The transmitter becomes an imaginary anchor, right? And instead of doing a ranging with the anchor, we are simply measuring the RSSI or the RSS. Okay, so from the RSS, can we estimate the distance, right? Because there is clearly an analytical relation with distance and the received signal strength value. So why not use that thing and try to compute the distance? Okay, so often we call it, like as as I told you earlier, log linear path loss model. So the distance is in the log domain, and RSSI is equal to slope multiplied by distance plus the intercept, right? This is like y is equal to mx plus c relation. Okay, and from this equation itself, right, you can estimate the distance given RSSI for RSS. Okay, so if you are given a certain value, right, of the RSS that you have measured at a certain distance from the anchor, you can go back to the calibration model that you have generated for that particular link, right, for that particular system, right? What is the how the RSS changes with distance? You can go back to this plot and simply refer what is the distance, right? So if you get this value, let's say minus 30, your graph or this particular model is going to tell you that okay, this is where minus 30 intersects, right, with the straight line, and your distance is like something like 6 meters, right, some 6.5 meters. Whereas this particular thing could have just a sample drawn from this data set, and your actual distance would be simply 4 meters, right? So as you are understanding that this is a fit that is done based on ordinary least squares, and there is a possibility that there will be some errors that will be introduced into this, because this data will be highly noisy. Okay, this is simply a trend that we can observe, right? The linear trend we can observe with RSSI and the logarithm of the distance, but there will be a lot of outliers, and particularly the outliers become more and more with distance and obstacles, right? So the actual RSSI or the actual RSS that you see is not just the path loss, right, but also there are other components which are known as shadowing, right, which is some loss that are encountered because of the presence of obstacles. Okay, so when you study free space path loss, this is basically the signal traveling through the medium, but there are more things that are actually added to the total decay of the signal. One is called shadowing, and then there are random changes in the signal, which is basically due to constructive or destructive interference, right? This is often known as fading. Okay, so there are two more components apart from path loss, which is known as shadowing and fading, which contributes to the total RSS value that you actually see, right? And often these things are unpredictable, right? Or you need a very meticulous calibration of the entire system in order to do such prediction. Okay, so as you see from the RSS data, if you simply try to predict the distance, there is always a room for error, and this is expected because it's very difficult to have a very like a sort of very like correct model which captures the distance, which captures the RSS as a function of distance, right? The model could be extremely complicated, and if you try to overfit the model in a certain region, right, it might not work for some other direction, right? Let's say if you have the transmitter here and you want to model any receiver that comes in this straight line, right? Let's say this is RX1. You have like very meticulously modeled how the signal decays in power in this direction, right? However, if you have a receiver which is in this direction, right, RX2, the same model might not be applicable because the obstacles here are different, the reflection patterns here are different, right? So this is not going to be directly copied, so or cannot be directly used. Okay, so what we do is that we create a general model which gives you some accuracy, right? You can get a vague idea about the distance, right, which is not totally wrong but correct to some extent. And you will see that is what all these BLE beacons, right, the Bluetooth low energy beacons do. So they will simply look at the RSS value, and from the RSS value they have calibrated the value of the range. So that is what they are going to use that as a range. And these are like off the shelf devices, like COTS means commercial off the shelf. So off the shelf devices that are available, which like this company called Estimate, that they already buy, they already sell these beacons, right? You can place these beacons on the wall, and they will give you a mobile application where you can figure out the signal strength, and that signal strength can be, they have a model to convert the signal strength into a distance. Okay, so this could be used for proximity sensing or localization, both of them, right? So in case of Estimate, what you need to do is that once you deploy this on the wall, you need to tell them what are the coordinates, right? You need to tell them the coordinates of these beacons. Okay, So then it becomes very much like your multi-iteration exercise, right? So it's just that the ranges are very noisy. Okay, so you do have ranges from 3 such beacons. However, the ranges are very noisy now. Okay, you might have several meters of error. Okay, so sometimes this will be used for proximity sensing only. Okay, so as you see, if the ST is moving away, how the distance is tracked, right? So it is an output that is given by the ST itself, right? So initially, this is the ground truth. So the actual means the ground truth distance. So if it is 0.5 for the first 2 minutes, right? So 0 to 120 seconds, this was kept at uh, 0.5 meters, right? Then it was kept at 1 meter, and then it was kept at 1.5 meters. So you could always see that initially there was some error, and the error sort of started growing, and then whenever you were more than 1.5 meters, the error was kind of large, right? The error was large, right? And in case if you keep the at higher distances, right, where your actual distance could be, let's say, 15 meters, right, and in that range it could be totally wrong, right? So there will be so much of obstacles, and the path loss becomes very unpredictable, right, at higher distances from the beacon, or higher distances from these anchors. Okay, so we have to see the regime, right, where how much this kind of technique works, right, in order to compute the distance from the RSS it's directly. Okay, so do you have any questions regarding the estimation of distance from the RSS itself? And these are devices that you can simply buy in Amazon, right? These are commercially available. Okay, so all they have is a Bluetooth beacon, and Android APIs already allow you to receive Bluetooth packets and look at the signal strength, right? So if you are using Android, so Android APIs, they will have very well documented. If you are interested, you can take a look at this. They have BLE related APIs where they will allow you to look at signal strength or RSS of Bluetooth packets. Yeah, I'm also going to show you how you can do it using Wi-Fi, right? I have a very small demonstration where you can use a Linux-based system to look at signal strengths of Wi-Fi packets, and then create a path loss model of your own. Okay, so this is the same thing, right, where you can get the RSS information from Wi-Fi, right? So how can you do it? You can use the Linux tool called IWList, right? You can either do it from your Linux laptop, Raspberry Pi, doesn't matter. And in IWList, this is a wireless tool where you can use a lot of different arguments, right, in order to get a lot of parameters regarding the the neighboring wireless access points and your communication channel and so on. So one of them is called scanning, and if you use this thing called scanning, you can actually get lot of details regarding the neighborhood access points and what is the signal level if you are receiving a packet from that access point. And that is what you are interested about. You are interested about knowing the RSS for a given access point, right? The received signal strength from a given access point. So they are called cells, right? So this cell you can simply ignore and think that this is an access point, and this is the MAC address, the medium access control, the hardware address of the access point, the MAC ID, and you can know some details like what Wi-Fi channel it is operating on, what is the center frequency of that channel, at 2.472 gigahertz, right? And you can also see the details regarding the signal level, right? So this is what we are interested about. So let's say here this one reads as minus 81 dBm. Okay, so minus 81 dBm is the received signal strength of the beacon packet which is received from the access point that has MAC ID, this one. Okay, and you can see all these things, right? The last beacon was transmitted 30 milliseconds ago and all these things, right? So there will be some beacon packets that the access point is going to transmit, and you can receive them to localize, or you can receive them at least to decipher the value of the signal strength, right? And then your job is to figure out the location definitely. Okay, so now I'll try to go through a small demonstration, right? So that you can also try it yourself. This is very easy because all of you probably will have access to a Linux based laptop, right? And you can simply recreate the demonstration that I am doing. So I'll probably fast forward some places, right? So you can simply do an ifconfig to know that your wireless connection is set up. So this WLAN means that you have a wireless interface, right? If you do not have a wireless interface, it won't work, right? So just make sure that you have a wireless interface, and that wireless interface is going to give you the values of the signal strength and so on. Okay, so if you do this IW list scanning, right, as I am going to show you. So this gives you a list of all the different cells or access points that are present. In this case, you can get as many as 10 access point related data. Okay, so if you can just want to again look at the command, this is sudo IW list WLAN 0. This is the name of the access. This is the name of the interface of the Linux system we have, and scanning is the command that I pass on to the IW list program. Right, so it says scan completed, and it gives you the details from cell 01 to cell how many you have, right? If you can have 50 access points around you, it will give you all the details regarding that, right? And in this case, you see that this is minus 64 dBm, right, which is sort of a high signal strength that you have received. Okay, so now if you simply have this command, right, what you can do is that you can write a program to capture this data, right? This is very simple. So this is a command line thing that you can issue from, let's say, a Python program, and the terminal output could be captured, right, by doing some parsing, right, that I have done, but you can do it on your like however you feel like, right? It's kind of a string parsing that you have to do, and capture the details of the signal strength data as well as the MAC ID, because you need to make sure from which beacon you are getting the packet, right? Otherwise you will be confused. Okay, so from which access point or which anchor location you are getting it. Okay, so now if I simply do a grep, right, that is what I'm showing here, you can filter out the data. Okay, so you can still use this address thing, right? And if you do an egrep of address, you can find out, let's say in this case you are looking at 5 unique base stations or 5 unique access points. So that's why you have these 5 addresses. Okay, so and if you also do a grep with the signal quality, so now you can see you have cell number 01, you have this ID, and then you also have the signal quality minus 58 dBm, minus 42 dBm. So maybe this one is very nearby, right? So that's why minus 42 dBm. Okay, so that is also something that we are interested about. We are interested about the address, where is the signal coming from, and what is the intensity of the signal. Okay, so that's why we have these numbers. Okay, and the idea is to estimate the distance using these numbers, right? This is an exercise, I think, which all of you can very easily do. Okay, so now what I'll show you is I'll fast forward the video. Okay, so I simply wrote a program like a script, right, which basically issues this command, right? And after issuing this command, it is going to read all the output from the terminal. Okay, so if you read, so you can write your own program to do this, right? But if you somehow parse this data, you can store all the access point specific signal strength in, let's say, in some data structure, right? Let's say in a dictionary, you can store them. Okay, and what I'm interested to show you is the plot, right, that I have shown you earlier about regarding the path loss is something that you can create, right? So whenever you do this, right, IW list scan, and you are trying to do a Python Wi-Fi scanning. So these are all the data that are being logged. Okay, so you can either log it or you can create a model, right? So after logging this data, you can have to create a path loss model by doing the linear regression that I told you and figure out the values of the intercept and the slope, right? That was our exercise. Okay, so this is something that where we are collecting data. So if you see, they are slightly fluctuating, right? Even at the same location, the value of the signal strength is not going to be exactly constant, right? Because of some fading issues and shadowing, they will continuously change. Okay, although nothing is changing apparently, right? That you are not moving the transmitter, you are not receiving, you are not moving the receiver. Still, you will see there is some fluctuation of the signal strength. Okay, and that is natural. That is something that you have to embrace. Okay, so now let's say you collect such data, and this data will be collected for some amount of time. Okay, and now what I am doing is that on the left hand side you see the access point is slowly moving towards our side, right? So the distance becomes more and more, and at the same time I am trying to plot the RSS value on the right hand side in the plot. Okay, so this, right, this is a real data set, and from this data set you can at least appreciate that there is indeed a relationship, right, that is linear, right? I have not shown it in the logarithmic scale here, right? I could have like written it in that way, but if you do this experiment yourself and try to plot it, you will indeed see a logarithmic in the logarithmic scale. You will see a linear nature of the path loss versus the log of that distance, right? And you can simply try to fit a straight line equation, right, or do a linear regression through those data set, right? And that will give you idea about how the signal strength changes as a function of distance, right? So this is your distance, which you can take as a, let's say, log of d, right? And at every point here, this is in 1d, you will basically register a value of RSS. Okay, so at every point here you will see some RSS, right? And what we are trying to do here, that when your distance is very close by, your RSS is high, and then it slowly sort of decreases, right? If you see the value, it is like minus 40 or minus 50, right? So you are having a path loss. Okay, so at higher distances your RSS value is going to decrease. Okay, and you can always fit this straight line. You can always fit this line. Okay, so then you can have a very simple localization system which is based on the data, right? So the data you have used to create a signal strength versus distance equation, right? And this equation can directly tell you what is the distance of the IoT device from the access point, right? So this is your IoT device, right, which is a Raspberry Pi here, and there is an access point which is installed here, right? So on top of this box I have kept an access point, right? So with increasing distance you have a very clear idea about the path loss model. Okay, so this is your path loss model, and the bad part is that you have to do all this calibration exercise in order to create this model. Okay, so this doesn't simply come out of thin air, right? The way we were doing the ranging, this ranging works everywhere, right? Doesn't matter where you take it. Whereas this path loss model is very specific to the environment, right? If you do not have this wall, right, this is going to show a different pattern, right? If you don't have this, let's say, this wall, right, this is going to show a different pattern. So it's very, very specific and very sensitive to the environment, right? So if you are deploying a Wi-Fi localization system which is simply based on signal strength RSS, you have to do this extensive calibration exercise, which is sort of painstaking, right? So that is the case with any of these data driven techniques, where you have to put a lot of effort in collecting the data. Okay, so as I told you, right, if you have this Wi-Fi access point, and you the idea is to capture the RSS in different locations. Now the intention is to use this RSS in order to figure out the location. This RSS will be used to figure out the location. Okay, so earlier we were trying to figure out the distance, right? We are now trying to scale it up and kind of understand that how RSS will be used to figure out the location itself, right? So here the location could be simply discrete chunks of space, right? Contiguous physical space, and we are interested by seeing the RSS from which place in the geographical area this RSS could have been produced. Okay, so that is our intention or exercise, right? And if you simply go to 6 different locations and capture the signal strength, and this is an histogram of the data, right? You have already seen that this data fluctuates. You can see in some places it is relatively smooth, right? So here, if you see the variation of the RSS value from -72 to, let's say, 65, right? And it's mostly concentrated in like 4 or 5 dBm, right here. So there is not much of a, like, there is not a huge variation. And whereas if you see this location number 6, this is pretty wide, right? And not only 6, but also 5 or 4 or 3 or 2, right? For that matter, 2 is a little bit constricted. It is like -20 to -15, whereas in this case, this is -94 to 84, right? -84. So it's fairly a wide sort of a distribution, and this is going to bring in a lot of uncertainty, right? So particularly in the last exercise, where we were trying to compute or estimate the distance just based on the RSS itself, if you see, there was a lot of error that was introduced by trying to fit the straight line, right? So even for the same distance, even for the same location, you can have so much variation in the RSS data. Okay, so what you need to appreciate is the variation. Okay, and this is something that you can't help, right? This is something that happens because of shadowing, fading, and path loss, right? It's sort of definite, but not that definite. Okay, so, and if you do have a lot of obstacles, the uncertainty increases. Okay, and there are like a few reasons, right? One is that if your signal strength is very poor and you have lots of obstacles in between, right? If you have the access point on the ground floor, and let's say your devices are on the first floor, so the signal path covers a lot of obstacles. There could be people moving around. There could be other interferences from different sorts of devices, right, which are operating in the same band, right? Otherwise, you will not have an interference. This also contributes to the variability of the RSS. Or you can have like people moving around, right? So if there is a person who comes in between the device and the access point, this is going to create a certain drip, right, in the signal strength, right? Or the power will be absorbed by human bodies. Okay, so you can artificially think that the device has moved to a greater distance, but this is not the case. This is simply because of introducing a human body in between, in the link, right, or in the channel. Okay, so these are the different reasons where the RSS could vary with time. Okay, so one of the method that we follow here, right, because whatever be it, right, we need to sort of model such a system. We call it RSS fingerprinting. And what is RSS fingerprinting? We are assuming that this distribution is unique to this location. Okay, instead of looking at a single value of an RSS sample, we are trying to assign a distribution for the location. Okay, so whenever you go to a certain location L, you will see a certain distribution of the signal strength. Okay, and then as long as the distribution is unique, right? Let's say you want to fit a Gaussian to this data that you have observed, so you can always have a mu, right, which is basically the median, and the sigma, right? So these are the two parameters that we associate with a normal distribution, right? And this could be given a location Li, right? So given a location Li, you can have a mu I and a sigma I. Okay, so now if you have n such locations, the idea is to create a model for n distributions, right? So whenever you get a bunch of RSS data, you can quickly check that which distribution is it coming from, which let's say maximum, what is the maximum likelihood that it is coming from the distribution Lk, right? So we can choose whatever location creates the maximum likelihood, right? So in that way, the location could be classified, or the location could be identified. Okay, so as we see that this RSS, right, to distance mapping is not unique, or it's giving a lot of error, right? We resort to basically RSS maps, and using this signal strength maps as like location features, right? So instead of having one, you can have multiple, right? Because this RSS could be coming from multiple access points. So this is coming from AP1, whereas this is coming from access point N, right? Or access point N. So you are having a feature of length N, right? So this is an n-dimensional feature vector, right, which could be associated with a certain location L. Okay, so instead of having single dimensional distribution, right, the Gaussian distribution that we are talking about, now you can have an n-dimensional Gaussian, and this n-dimensional Gaussian will be associated with a certain location. Okay, and these locations could be discretized now. Okay, it could be contiguous, but just to reduce the number of separate classes and try to make it a little bit more meaningful, right, in terms of our localization application, we can always have discrete classes of location. Okay, so we can control the granularity, right? Let's say we want to resolve locations of, let's say, 1 meter by 1 meter, right? So if it is within this 1 meter by 1 meter, I am happy, right? I don't want to have a more fine-grained resolution. Okay, so every such box, right, every such box here will be associated to an n-dimensional distribution, right, n-dimensional Gaussian, let's say, and this n will be the number of access points or number of reference beacons that you can place in that location. Okay, but we are not trying to estimate any distance from them now. And we have already seen that if you take that route, you have to put excessive calibration effort, and it might go wrong, right? Because there is a lot of temporal variation and so on, right? So instead of directly capturing the distance, we are trying to create a mapping of location and signal strength, and we do not make any assumptions about the linear fitting, the ordinary least squares by which we actually fit a straight line to the path loss equation. So we do not make any such assumptions. We just let the entire signal map be free, and all we are trying to understand is learn this map, right? Learn this database. Okay, and whenever there is a new sample that arrives, we just want to check, right, which one of the distribution it is likely to go to, and that becomes our predicted location. Okay, so in this case, as I show, if it's a building map, we'll basically have the signal strength models, we'll say. Okay, so for every such locations, we will have these distributions, and these distributions will go into some kind of a database. And as we said, there will be discrete locations. So it could be like L1, L2, L3, and dot dot dot. Let's say there are Lk such locations. So this k could be very large. It could be like 100 such locations, 200 or 300 such locations, and you will also have n reference access points, right? Mind that you do not need to know the location of the access point in this case, the way we are describing it, right? So there could be 1, 2, 3, 4 up to n minus 1 and n, right? There could be n access points. So for these n access points, you will basically have this n dimensional data set for a given location. So these are the, like, this is feature 1, this is feature 2, right, and this is feature 3, and so on, right. At the end of the day, you will have this feature of size, the feature vector of size n, which corresponds to location L1, L2, L3, dot dot dot. Okay, so I hope that this fingerprinting idea is clear in your mind. What is the fingerprint? The fingerprint belongs to a certain location. Okay, so it is Li's fingerprint. Okay, so like the way you give biometrics, right? So this is your fingerprint. So this is the location's fingerprint. Okay, and what does the location's fingerprint consist of? This consists of the signal strength distributions from these n access points. Okay, that is, in the machine learning literature, we call a feature vector. So now, if you really want to extract, let's say, certain parameters of those features, it could be, let's say, as I told you earlier, it could be mu and a sigma, right? These are the two parameters that are enough to generate a normal distribution, right? Or you can have other features of your choice, right? Whatever you want to create from the distribution, right? Whatever information or metric that you want to create from a certain distribution, you can keep that, right? There is no restriction. Okay, so in an essence, right, what we are creating or what we have created is known as the fingerprinting database. Okay, and now this is the standard way this method is applied. You have this fingerprinting database, so this is the DB. Okay, and from the DB, either you can create a model, right? And whenever there is a query, right? So this is a query that comes to the system. It says that, okay, I have this and this RSS values. Can you tell me the location? Okay, so this is the localization problem now. Okay, so earlier we were dealing with the ranges, right? I have these and these ranges from these and these anchors. Can you tell me the location? And we did a lot of analytical exercise and tried to figure out the location of the device using multilateration. In this case, the thinking process is a little bit different, right? So we have a signature database or a fingerprint database, and from the database we try to ask the question that this is my RSSI pattern. Can you tell me what is the likely location I am getting this signal from? Okay, and the answer is basically the location you are at. Okay, so either you can go via a parametric model, right? Let's say you want to create some distributions and use some parameters for those distributions, right? Let's say the Gaussian example I was telling you, right? You can always create a Gaussian naive based system, right? So this would be a naive Bayes sort of a classifier, right? Gaussian classifier, right? Which is going to give you the class with maximum likelihood where this query is coming from, right? So what will this do? It is going to check with all the classes, right? All the locations will be classes now. So all the locations, these are all classes, right? And for all the classes, you will have a prior knowledge, right? The prior probability, and then you also have a likelihood function, right? So given an RSS, what is the likelihood that this RSS belongs to this distribution, right? You can always have a likelihood value, right? So from that you can calculate a posterior probability of a certain query belonging to a certain class. Okay, so you can create your own localization prediction, location prediction system using this kind of a tool, right? Or you can even have non-parametric things like k nearest neighbors, and k nearest neighbors is actually applied in one of the first papers, right? That actually used this concept of fingerprinting for localization, right? This was long back in the year 2000. Just for a historical note, I am introducing this paper. This was from Microsoft Research. They you can, like, it's a very easy read. It's nothing complicated. There are no fancy or very scary formula in the paper. I would request you to take a look at this paper. and they say that it's the world's first Wi-Fi signal strength based indoor positioning system. Okay, so what they do is that very simple. There is no distributions or anything that are involved, right? What they do is that from the fingerprint database, they had like k access points, right? I'll quickly explain you how the system looks like. Let's say you will have let's say 4 or let's say 5 access points, right? So there will be AP 1, 2, 3, 4, and 5. So whatever data, right, the signal strength data that you will collect at a certain location, this will be a 5 tuple, right? So it will be an RSS 1, comma till RSS 5. Okay. So and for every location, let's say you preserve this. Okay, so your fingerprinting database looks something like this. L1 is this, L2 is something else, right? L3 is something else, L4 is something else, right? And you collect all this data and create the DB, right? This is the fingerprinting database. And what this radar authors have done is that whenever you get a certain RSS query, right, RSS1 till RSS5, and you are interested in knowing what is the location for this particular data set, right? What is the location for this particular feature vector? Okay, so you simply do a k nearest neighbor search, right? That is one possibility. There are many ways to do it. So just for historical reference, they have used k nearest neighbor. So they are going to simply compare the distance of our feature vector with all the feature vectors in the database. Of course, this is a costly operation, but that is what they have done. And then take the top k matching ones, right? So you can always look at what is the distance of RSS1 with this RSS1, RSS2 with this RSS2, and so on. And you can take the Euclidean distance. So that is how you can say what is the distance between L star and our L1. And you can find out L star versus L2 and so on. L star versus, let's say you have 1000 examples in your DB. So you will basically get some distance matrix, right, from D1, D2 to D1000, and choose the top k, right? Let's say your k is 3, so you'll choose the top or basically here the nearest neighbor. So you'll choose the bottommost values, right? Let's say D57, D79, and D112, right? So let's say these are the 3 nearest neighbors, and you are also, these are the locations that are associated, say L57, L79, and L112. And their Euclidean Cartesian coordinate. In the Cartesian coordinate space, their coordinates, right? Their x and y values. You can simply do an average and figure out what is their location. Okay, so this is not using any parametric distribution per se, but simply using this non-parametric approach like k nearest neighbors, right? I would highly recommend, right, to at least read this paper if you want to gain some insight about how fingerprinting database is applied for this localization system, right? So this will give you a lot of insight, and as you understand that from the number of citations, right, so many people have referred to this paper. This is one of the first and simple system which gives you a very nice tutorial in order to understand the nitty-gritty details about how this system could actually work, right? It might not be might not be a very practical system, but it is a very good tutorial in order for you to understand how the system might work. Okay, and the other problem sometimes you will have is about the Rss prediction, right? So you might not have a complete map like this, right? On the right hand side, I have shown that all of these data points are filled, right? In all these small boxes, you have some data to start with. So often it is the case that you do not have any data to start with, right? Some of them could be void, right? You have not collected data by going to that location. So sometimes sophisticated interpolation methods are used, right? So the locations could be either contiguous, right, like this one, or it could be discrete, right? But the problem is that if you have a certain set of locations where you have data and there are a certain set of locations where you do not have data, can we predict the distribution of the RSS in such data in those places, right? So that when you try to do the location prediction, it might happen that your RSS belongs to some of the places where you do not have previously collected data from, right? So another important problem here is to know from a given set of data points what are the possible RSS values which could be in locations where I do not have data, right? So in, let's say, in some of these places I do not have data, so I need to fill up these voids, right? And we have to do it accurately such that my location prediction is sort of better, right? So this is more of going from location to RSS, right? So that whenever I get an RSS like this, I can go back to this location. Okay, so this is another sort of exercise that we often need to do if we have incomplete data, and which is often the case, right? We cannot have RSS for every possible location in that geographical area. Okay, so so this is the, on the left hand side I show that, okay, maybe these are the few locations where we have collected data. Let's say 1, 2, 3, 4, and let's 5 and 6. Let's say these are the 6 locations where we have collected data, and from these 6 locations, can we create this map, right? Can we create the map for all such locations, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this is 10 cross 10, let's say, right? So you have 100 such locations. So from the 6 data points, can we predict all the 100 locations, what will be the RSS distribution there, right? So I'm not saying you have to do at this ratio, but if you add more and more data points, you have to put more and more cost, right? Because collecting such data requires human effort, right? And once you do this RSS value prediction for all such 100 locations, so this is like a let's say 10 cross 10 grid, right? Once you do that, right, you can very easily start localization, right? So whether the localization is accurate or not, that is a separate question, because that depends on the quality of your prediction. Okay, so if your prediction is good enough, if your RSS prediction is good enough, your localization will also be good. Okay, so we did cover localization in some details, right? We really covered a lot of details regarding the ranging part, right? Where I already told you there is a lot of things that we understood regarding how ranges is calculated and multilateration, and apart from that, how MDS is used, as well as some ideas about fingerprinting, right? And in particular, we looked at RSSI, right? Right, and whereas you can also use other things which are more elaborate features, right, like channel state information particularly, right? So we are not going into this kind of details, but let's say if we stick to a very simple feature like received signal strength and build a database of the RSS values with location, this is a very simple system which could be used for doing localization, and this is something that you can simply try out, right? I already showed you a very small demo, right, where you can extract how you can extract the Wi-Fi signal strength, right? And this is also something, if you are acquainted with Android, Wi-Fi signal strength APIs are already present, right? You can even store such values in your mobile phone, right? Through your mobile phone, you can read those values, and you can create a path loss model, right? You can calibrate a path loss model and try to see it for yourself, right? How the signal strength changes with distance. Okay, so I will keep the class till this much, and